A big welcome to everyone, and thank you for taking time to attend our meetup today to learn more about PingCAP and how TiDB and TiKV are helping customers accelerate their digital transformation and business growth. Just a quick thing about myself. I'm Fadi Azari. I run marketing for PingCAP in North America, and I'm delighted to be your host for this meetup today. We have an exciting set of topics and speakers joining us today, as you can see from the agenda. I would like to welcome our PingCAP speakers, Huang and Kolbe Kegel, which I'll get to in a second, specifically in the agenda. We will start our session by listening to our customer with a short video from Databricks' Reynold Xin. He's co-founder and chief architect, and he'll be talking of Databricks, and he'll be talking about why they chose TiDB. This will be followed by Huang, our co-founder and CTO at PingCAP, who will cover PingCAP and TiDB, the vision, the product strategy, and our differentiation and approach to our product. We will top it off with Kolbe Kegel, customer success engineer at PingCAP, who will be going through to demonstrate TiDB in action. With that in mind, I also want to encourage attendees to ask questions in the chat all along. Please do. We will have a swag, a TiDB t-shirt, to send out to people who ask questions, a certain limit number. We will have TiDB experts to answer those questions, and we'll also have a live Q&A session at the end. With no further ado, I would like to start the event. So please welcome Databricks' Reynold Xin, co-founder and chief architect, in this short recorded video to learn more about why Databricks chose TiDB.
Hi everybody, I'm a Databricks co-founder and also known in the open source community as the top contributor to the Apache Spark project. I'm also wearing a vintage Databricks t-shirt today. This is actually our very first logo, so it's not the logo you would find if you go Google Databricks. It's not even the previous logo, but a logo from 7 years ago. It's really an honor to be here, as PingCAP and Databricks have a lot in common. And I've been observing the growth of TiDB and PingCAP from afar. We're both started by founders with deep data infrastructure background. We both have deep roots in open source, and we're both born cloud native. At Databricks, we've been observing that the world is generating more data than ever, both online and offline. And Databricks itself is a prime example here. So Databricks is going through a rapid business growth phase. For example, we started the year 2020 launching roughly 1.5 million virtual machines in the cloud each day. And we ended last year at over 5 million. So you heard it right. It went from 1.5 million virtual machines a day to over 5 million a day. And that's a 3x year-over-year growth. Coping with this growth is a big challenge to our infrastructure, our operations, and our team. One particular challenge was to scale the database infrastructure to store and analyze the data generated by these millions of machines. And like many other companies, we rely primarily on MySQL as the main online database. Storing all those in MySQL has been very difficult as there's high operational load to scale MySQL beyond a single node. Last year, we started looking at what alternatives we would have to replace MySQL. First and foremost, we wanted a cloud native and, more importantly, multi-cloud solution. And that means we can actually easily port from one cloud to another because we operate in all three major Western clouds: Amazon Web Services, Azure, and Google. We don't want to be locked into the cloud provider's specific stack in order to get maximum agility. I wanted a solution that's open with a community-driven development approach. And last but not least, as a table stake, the ability to scale with minimum operational load from our engineers. So we started experimenting with TiDB, and it really surprised us. It took us only about a week to get all the application level changes needed to migrate from MySQL to TiDB, thanks to the MySQL compatibility. And we're really impressed by the cost efficiency we're able to achieve going from one version of TiDB to another. So we got a big boost going from TiDB 3.0 to 4.0. We got another big throughput boost going from 4.0 to 5.0. And as an engineering team, we're also really impressed by the rigor in testing the TiDB community have invested in because it's extremely important. We cannot afford to lose data. But what's really attractive here is also the ability to add nodes and more nodes dynamically with the system as business demands increase. So now the tech stack and the infrastructure can scale with the business. And now we're about to put our first service running against TiDB into production. In parallel, we've also been looking at how we can run analytics directly against online data through TiFlash and TiSpark integration. And this is really cool because we're able to serve our customers analytics queries on those real-time online data started by the virtual machines. And our belief is that TiDB will support the rapid growth of Databricks as a business and allow us to run faster in the future.
Thank you, Reynold. As you heard from Reynold today, Databricks is keen on using TiDB to help address their scaling needs, not only for today, but into the future for their data platform to really empower their end customers in their digital transformation, their own and their own customers. I would like now to welcome Ed to share PingCAP's vision and strategy. Ed, please take it away.
Sure, thank you. Thank you. It's really glad to be here to give introduction and some technical vision about PingCAP or what we think about the technical trend of database. Okay. So today my talk will be a little bit technical, and I think if you are a database user or database engineer, maybe you will like it. First of all, I want to do a very quick introduction of myself. My name is Ed. I'm the co-founder and CTO of PingCAP. And I myself, I consider myself as still a software engineer. I think I'm still coding or reviewing code every day. Yeah, and my interest is in distributed system and database system. And also, I also play guitar, and I have my own band. Okay, and I also a big fan of open source, and I think my previous projects like Codes, like TiDB, like TiKV are all open source. So I am a true believer in the open source and community. So a little bit about PingCAP. PingCAP is the team behind TiDB, and we built TiDB from ground up, just like Databricks and Spark. And okay, so and the PingCAP provides the enterprise level and the cloud-based service for TiDB. I think that maybe some of you have never heard about TiDB before. I would say TiDB is a young project, but it is widely used in open source community, and a lot of big company are using TiDB in production, and we see that the trend and the community is growing fast and very healthy. Okay, this is some of the users of TiDB, and I think beside this logo here, we think there are more than 1,000 in production users using TiDB every day. I just mentioned that TiDB is a young project, and PingCAP is also a young company. So we started 6 years ago, and now we have it's a PingCAP just 6 years ago. We started from 6 years ago, and I think we did a good job in last past 6 years. Okay. Next, I want to talk about the tech. For you, if you haven't heard about distributed database or database, I want to give the very quick introduction of what is database, what is distributed database. I used to use a metaphor. I always say, hey, database is very simple. It's just like the container of data, right? So let's think about the water the data. So the bottom, the container of the water is the database software. So and the distributed database is also very easy to using the same metaphor is very easy to understand. So I think there are two methodology to build a distributed database. One is using something like sharding technology to, if you have a lot of water to store, you may have a lot of bottle to keep the water. But maintaining a lot of bottle is very painful, right? So another methodology to build a distributed database is to build a elastic, huge bottom to store water. So yeah, it is two kind of the way to build a distributed database. I will talk about these two directions in next few slides, and the pros and the cons. Okay, but why distributed database or why TiDB, right? Because we think that the enterprise are growing very fast today, but the infrastructure, I think they are facing a lot of challenges in the infrastructure level. Like maybe today we just invented too many databases. Like we have time series database, we have graph database, we have Hadoop, we have MongoDB, we have MySQL, we have Vitis. A lot of database create the data silos. I think it's very painful to maintain a lot of data stack or technology stack within the enterprise. It's very, because it's very a lot of system is the data synchronization will be a big problem across different data sources. The second, I think nowadays everything is web scale, right? So we have to handle the unpredictable traffic. So that means the data infrastructure or your application infrastructure should be elastic scaling. That's not very. It is a very high standard for a lot of database or systems. Yeah, I just mentioned the maintenance cost. So I think if you are running a big company or you are running the fast-growing company's infrastructure, you may be have the same feeling about what I put it here. Okay. Let's focus in database part. The challenge, I think, under the hood is because one of the root cause, I think, is the separation of OLTP and OLAP. And we have too many databases, but some of them are focusing on OLAP workload, but some of them are OLTP database. But synchronize the data from OLTP part to OLAP part is you have to build a lot of pipelines, like introducing another systems like Kafka, like parser to build the data pipeline across different data source. That is very, I think that's painful, right? And also another big trend is people are moving to cloud, right? So because maintaining the own infrastructure is painful because cloud vendor or cloud service provide a fully managed service for the normal infrastructure. That is good because user experience, right? But from the database part, I think something never changed is the SQL never dies, right? Because if you notice past 10 years, a big trend is that every infrastructure, data infrastructure, software, more or less they will provide the SQL interface to the user, because I think nowadays we have a lot of legacy codes, legacy application are using Oracle, like using MySQL, using Postgres. If you want to migrate to the new infrastructure, new software, new database, if the database doesn't provide SQL interface, that will be really painful. Okay, so the SQL is a must for still a must, I think, especially in the future. Okay, so in the world is my point is right now everything is web scale. You have to have the scalability in different layer and the different abstraction of your infrastructure stack. But nowadays, our infrastructure world is fragmented. So what we can do and what TiDB think about how to fix that. Before talking about how we dealing with the situation now, I want to say why now? What has changed? Why not like 20 years ago? Because it is why now? Why 6 years ago we decide to start our own business to fix the problem? Because I think past 10 years the industry we did a great job in made a great progress in creating new hardwares like the network cards, like high-speed SSD. So I think past 10 years we made a great change in the hardware industry. So we have the foundation to build a distributed system, like to get a balance between the performance and scalability, right? So, for example, nowadays within data center, your bandwidth is big enough to feel like you access the remote disk just like access the local disk. The throughput is I think the throughput is even higher than you're accessing some local disk sometimes, but latency is a little bit higher, but I think it's acceptable nowadays in the modern data center. And also more in the software part, we have a lot of new technology, new algorithm like Paxos, like Raft, that makes us have the foundation to build a high availability, scalable system. And I think also like Spark, like some distributed MPP database like Greenplum brings they have did a great job in creating a distributed computing framework to make SQL. SQL is just like it's a language, but how to combine the distributed system and the SQL together to leverage the computing resource in the cluster to analyze data, right, using SQL. So a lot of new technology and new algorithm to we can have them to build a modern system. Okay, and of course the cloud. I will not to talk more about the cloud. I will live in the next part. Okay, of course. So today I will talk about some next part I will talk about some we have the hardware, the software, a lot of new technology to as the background, how we can put them together to build a new system. That what's the frontier of the distributed database design, and what is the challenge nowadays or in the future. So this is my I will talk about this topic in next few slides, like the data distributed strategy, replication strategy for the high availability and data consistency, and transaction, how to get the ACID compliance and the transaction support, and the query processing. And I will talk about the challenge we're facing, like how to dealing with the hybrid workload, or how to build a cloud native architecture for database. Okay, first, data distribution. Right, the first big problem or big question for the database designer is how to distribute the data, because you cannot put all the data into one physical node. So right, because we are building a distributed database. So choosing the data distribution strategies is very important. I put it in. I think in general we have two ways to to make the data sharing strategy or data distribution strategy. One is static, another is dynamic. I will put it in the example, like if we have a table like this, the user ID, the location, name. The static sharding strategy is really simple. For example, we can choose a column, or we can choose a sharding key, and to split the table into different table by using the sharding key, using some hash function or another. For example, in this case, we are choosing the location as the sharding key. So the Seattle will be placing in one node, the Washington DC. The data with the location of Washington DC in another table, like New York. So this strategy, why we call it static, is just because the before we sharding, we have to choose sharding key, right? But what if the static sharding strategy have the good parts is we can have a strong data correlation, right? For example, if we just want to, our queries just happen in, for example, we have the sharding key, like we want to count star from all the data in Seattle. So all the query, all the workload will happen in this shard, right? So that means this strategy have a strong data correlation, and also it is really easy to implement it, right? So for example, using this strategy, the database is Wittis. I think Wittis is create some kind of middleware to do that, to choose a sharding key and split redirect the data, split the data according to the sharding key. But on the other side, the bad part of this methodology is like you have to application have to choose some column. That means the database should have no the application logic. That is not very that means you have to design the sharding strategy. Another big point is data screw, right? For example, if you choose the wrong sharding strategy, like for example, you have tons of data with the location with Seattle, but you have just one or two records with the location in Washington D.C. That will make the data screwing, right? And using this methodology, another big problem is that sometimes you have to choose for example, sometimes this kind of system are like middleware, so it is built on top of the database. So the resharding, the rebalance have to rely on the underlying database. Like that's very complicated to build a very flexible dynamic rebalance. For example, you have for example, if you want to reshard your data using another column or another sharding key, you have to move the data around, and it is very complicated. Yeah, because the different storage node, they don't have the global picture of the whole database. For example, you cannot do the transaction across different MySQL without the centralized transaction management. So that means you can very it's really hard to build a strong consistency and a robust data rebalance system using this methodology. But on the other way is using some I call it dynamic sharding strategy. But it is very hard to build a elastic scaling or dynamic data sharding strategy for relational database. I think before PingCAP, before TiKV, before I think before Spanner, I don't think in industry we have implemented, we have combined the dynamic elastic scaling with the relational model. I think relational model is not very friendly to distributed system, right? Because in the age creating relational model, we don't have a distributed system, so the design is just not very friendly. So, but how to fix that? I want to quote a saying from David Wheeler: all problems in computer science can be solved by another level of abstraction or indirection. So our in TiDB, or I think in today's state-of-the-art distributed relational SQL database, we use the same method or the same methodology. Is we mapping the relation model to the very flat, huge key value form or key value map, right? We are not, because relation model is very complicated, very it's not very friendly to the distributed system. But building the distributed key value database is not that hard, right? So our thinking is that why not we make under the hood, we store the data in key value format, but make users consider it is a relational database, right? So we can carefully design the encoding of the key and store the record data into the value part, but and we create a translation layer to make the key value pairs organized to show to present as a relational database. Okay, so that's the problem. That's the strategy we choose. So the problem will be sharding to make the data distribution strategy for the key value database. So the key value database, sharding for the key value database is a solve the problem. A lot of systems have done this before, like HBase, like Sandra, like DynamoDB. So the problem is what's the strategy we choose is, the key design point is we choose range-based sharding or the hash-based, right? The range-based is this hash, like for example, the key to use a hash function to get a result and using some consistent hash or some model operator to decide which store to keep the record. But the range-based sharding is we create the range and different ranges in charge of the different range of in different nodes. Okay. So in my mind, if you want to build a relational database, I think using the range-based strategy is a good way to choose. Yeah. Because in the real world use case for the SQL database, a lot of workload is like select star from the table or the table scan. Table scan is a very normal operator or very normal operation for a SQL database. So choosing the range-based data sharding strategy will have a better performance compared to the hash-based, because hash-based data sharding method is really friendly to some write-heavy or random write-heavy workload, but it will sacrifice the read workload or the table scan performance for a database. So yeah, we have made a trade-off here. Yeah. Okay. Under the hood, building the dynamic sharding strategy is, I think the key is that to create, when we choose the range-based sharding, how to do the dynamic data placement. I think the key is in TiDB, I think the key is to create 4 key primitives or operators. If you carefully implemented this 4 atomic operator, you can have a very robust data scaling or data placement foundation. It's split, merge, clone, destroy, just 4 operator. Yeah, it's not very hard to understand. I will put an example. For example, if you the split and merge is very easy to understand, right? When a range, for example, we have a continuous key value pairs, we call it a range A. For example, the data within the range A is bigger and becoming bigger and bigger, and exceed a threshold like 96 megabytes or 500 megabytes, something like that. we can have a split in the middle of the range to make it two different range. And on the back, on the other side, on the other way, when you have some operation like delete range, you can have the merge operator to move two continuous neighborhood range back to one range. Yeah, this split and merge. And clone and destroy, I will use an example. For example, we want to move the range A to another nodes like this. First, we have to create a new clone of the data of this range, and destroy the old replica in the or the old copy in the original node. So the result is you can see the data movement. That will define the data movement. Yeah. Okay. This is data sharding strategy. We choose the dynamic and using 4 primitives to create the elastic data movement and dynamic balance. And the second big problem is consistency and high HA. I think in distributed environment, the only way to ensure the data durability is to create more copies of data, right? Because every physical node have the possibility to, anything could happen, right? For example, the crash, the disk is corruption, yeah, the power outage, something like that. So the only way is create multiple copies, but the problem is how to keep the consistency across different copies, right? In the old days, for example, we have MySQL. We are using the old way is the source and replica, the leader and the follower replication. And the MySQL introduced another way to do the replication, call it semi-sync. But I think it is not fixing the very important problem, is because the leader and the follower replication cannot fix the split brain problem. For example, if you want to keep the two database with strong consistency, but the only way is that you every write have to write. You have to get the ACK from both two database. For example, when you have a write, you have to get the or the database flat safely stored the data. You can return back to the users. Hey, it's okay. But in this case, you sacrifice the availability. For example, if the network or the synchronization link is crashed, you cannot provide the service on both data center in this case, because when you have to, when you accept write in different data center, you will have the inconsistency snapshot for your data. Okay, this is split brain problem. But in academic world, we have some modern consensus algorithm to make a balance between the consistency and the availability. We call it RSM. Okay, the replication state machine. The popular data RSM algorithm is Raft and multiplexers. I think under the hood, they are just the same thing. I just think Raft is a simplified version of multiplexers. So it's basically it's the same thing. Okay. I will not drop too many details in Raft protocol, but I would say it is it's a modern data replication model with the automatic self-healing ability, or and have a good performance compared to if you want to have a strong consistency. Yeah. Okay, because safe shutdown is really hard. Okay. And but how to keep the, for example, if you build a consensus, for example, like we back to the data sharding here, we split the whole key value map into different ranges. Every range is a data replication group, but the problem is how to keep the data consistency across different range, right? Because, for example, range 2 have nothing to do with the data consistency with range 1, right? Because they are owned by the different replication group. Okay, but the only way to keep the strong consistency across multiple data range or in different nodes is two-phase commit. This is the only way. We don't have another way. I think some people may challenge me. Hey, there is 3-phrase commit algorithm. There is, like 1-phrase commit, something like that. But I think 3-phrase commit is just another way to. It's basically is a 2-phase commit. It's a optimization for 2-phase commit, the trivial 2-phase commit algorithm. So today, the only thing we have in the academia world is 2-phase commit. Yeah. But the 2-phase commit is sacrified consistency. Not consistency. The performance. The latency is a big problem of 2-phase commit. So the normal way is to build the 2-phase commit on different ISM group, the data replication group. Yeah. So the big challenge I just mentioned, one is the biggest challenge is latency. In past 3 years, I think I spent a lot of time to create a lot of optimizations in our transaction model to make 2-phase commit protocol faster. I think Spanner have a very creative way to use hardware to, like the atomic clock to allocate the timestamp. But we don't have true time. We don't have the atomic clock in the open source community, right? So we have to build a software clock to get the performance, the latency, get the balance of the throughput and the latency. So in TiDB, we choose we create new algorithm in TiDB 5.0. We combine the 2 different algorithms, like percolator. Percolator is also another paper published by Google, introduced 2-phase commit algorithm in the key value data store. And another good paper is a good way is HLC, hybrid logic cloud. I think CockroachDB using HLC for their transaction model. In TiDB 5.0, we combine these two model together to create a new kind of two-phase commit. I will to support our local transaction. I will not jump too much details here. If you are interested in this, you can follow our blog. I think I will write something about this in the near future. So I think there are a lot of ways to make trivial two-phase commit performance better. Yeah, so the result is the performance is acceptable compared to the traditional database. Okay. Well, query processing, a big topic. I think from a very high level, the SQL query processing will be divided into 3 layers: SQL parser, optimizer, executor. But when the SQL database compares to the combining with the distributed system, I think the parser is not the key point. The key point is how to make the SQL optimizer and the executor distributed, right? In the cost function part, we have to introduce some new cost function like network latency cost, data shuffle cost, locality, consider into the optimizer. In the executor part, we have to introduce some distributed operator like the predicate pushdown or aggregation pushdown to leverage the computing power from different nodes. For very simple example in TiDB, for example, if TiDB handle the query like this, we have a predicate here and we have aggregation here. So the computing node of TiDB will push down the operator to the TiKV nodes with the specific data, because we just mentioned that the data is split into different range in different nodes, and every node can have a local data scan and get the partial result and aggregate in the computing node to get the final result. Last year, in this year in TiDB 5.0, we introduced a new processing mode. We call it MPP. It's not very hard. It is not very. We just introduced a new operator. We call data shuffle. So basically, it will create a distributed hash map across different computing nodes. Okay. Last part is I will give a very quick briefing about the challenge and the challenge here.
It's like this sensation in the mouth.
Okay, good. Well, the first challenge is I just mentioned that nowadays the workload is becoming, I think, hybrid. You cannot tell the difference between in some case you cannot tell the difference between is it an OLTP workload or is OLAP workload. For example, sometimes you can just want to run. For example, if your database provides the full feature of SQL, like you can join, you can you can join, you can do some very complicated subquery, join, group by, and sometimes you just may want to run some query on your production database, right? But for example, like if you are running an e-commerce application, a website, you just want to see, hey, how much revenue we have made today. Some query like this. Yeah. So the quickest, the simplest way is just to run the SQL query on your transaction node database, right? But nowadays the best practice nowadays before TiDB is to move the data using some technology like ETL to move the data to another Hadoop cluster or the Snowflake or another data warehouse to run the query on our AP part. But why not we can have a single database to do the transaction and do the analytical on the same database? Yeah, this our if you have this kind of database, that will be very promising, right? So this is a it's a trend. We have a lot of HTAP hybrid workload nowadays, more and more. Another big trend is how to use the cloud native architecture to refactor the database. Yeah, I think Snowflake have a very good start, but I think it's just beginning. I think every infrastructure software will be reshaped by or refactored by the cloud infrastructure. So I will talk about HTAP and the cloud native a little bit. In the old days, just like I mentioned, ETL using a lot of separated data processing software to generate the report or do the ad hoc query. But you cannot just run in the AP query on your OLTP database because that will slow down your TP database. But the challenge is this architecture will bring the complexity for your data infrastructure. And another thing is that the data freshness will be another big challenge, because once you have migrated data to another database, that means it is not the same data. That will lose the MVCC version, the transactional information about your record. So sometimes there will be a big problem especially for some financial applications. So yeah, and nowadays everyone wants to know what's going on right now. Yeah. So how TiDB solved this problem? We just remember we created we split the data into many small ranges, and every data range is a replication group. In our we create a very unique way to solve the HTAP problem is we create the extra copy of every small data range. But the copy is a corner store. And yeah, so from the user's perspective, the OLAP, because our storage layer and the computer layer is totally separated. So the computing layer will redirect the AP query, redirect to the coordinate store, not to the row store. And the data in the in coordinate store, we call it type flash nodes. It is a raft learner. It will not involve into the OLTP part, but it is synchronized data in real time using the replication data replication mechanism. Okay. So the good point of this architecture is we separated the data replication into many data ranges, right? So it will not have a centralized data synchronization pipeline. It will separate it into many hundreds or thousands or millions of data group, the replication group. Okay, that will be scalable. And we can also leverage the different benefits from the different data format. For example, in columnar store, it is really easy to, really fast to, we can have a good performance for table scan, the operator like table scan. But in the row-based data format, we can have a good performance in, random index lookup. But in this architecture, we can combine these two benefit together. It is something the OLTP system or the separated OLAP system cannot do. The hybrid. So and also because I just mentioned the OLAP workload just only happen in the AP node. So that will be a good way to do the resource isolation. So last year I published a paper about TiDB's HTAP architecture. It said we have experiment here. We can see the OLAP workload will not affect the OLTP performance, but the same experiment happening MemSQL that will cause a big performance downgrade here. It's the experiment result. So another challenge is cloud native. I think I just mentioned the cloud infrastructure is reshaping the database infrastructure, right? For example, for example, the Snowflake is building the whole database on top of S3, right? S3 is a service provided by cloud. So that means you cannot, Snowflake is a software that cannot on-prem deploy on your data center because it is totally cloud native, because it's built on top of the S3 API or S3 service. So that's it's a great idea. I think I always said in last 5 years, I think the Snowflake's paper, the Elastic Data Warehouse is the best paper in last 10 years, I think, from my point of view. So I think that the same method will happen in maybe in the future in TiDB or in other cloud native data warehouse, because this is the diagram of the benchmark of S3. You can see the throughput of S3 is very good. Yeah, it is very elastic. Okay. Wrap up. So this is my today. All of the points I want to talk about. So some important topics, important problems lying in the industry, database industry, and in the future, the big problem or big challenge we have to face too. So my vision is in the future, we want to bring the database back to the old day, like 60 years ago. We don't have OLTP and OLAP at that time. Every workload can happen in the same system. So yeah, that will be very simple to the user, very easy to use. Okay, thank you.
Well, thank you, Ed.
Sorry. Yeah, a little bit out of time. Sorry.
Problem. Thank you, Ed. We've now heard from Ed about our vision and product strategy, and from also from our customer, Databricks, on how they intend to leverage the power of TiDB. So let's turn it over now to Kolbe, who will walk us through how easy it is to use TiDB by demoing our product. Kolbe, please take it away.
Hi, yeah, thanks, Fadi. So yeah, my name's Kolbe Kegel. I'm a customer success engineer here at PingCAP. That means I spend a lot of my time working with prospects and potential POCs and other people who are just trying to figure out how to make use of all that technology that Ed just discussed. So what I'm going to do is, well, first of all, I'm going to share my screen. Hopefully that's big enough for folks. If there's any concerns, just go ahead and say something in the chat. So I'm going to talk about TiDB in action. And here's what we're going to look at during this demo. The first thing I'm going to do is deploy TiDB cluster using TiUp, and we'll talk more a little about what that can do for you. After that, I'm going to start HA proxy, which is just a very simple load balancer, because we're going to have multiple of the TiDB server component, the SQL speaking front end. Then I'll start TPCC benchmark load just to put some action onto the cluster. Then we're going to check out the cluster status using our own built-in dashboard and the Grafana dashboards that we ship as part of TiDB. We're going to actually dynamically scale out the TiDB cluster to add additional TiKV stores and to add TiFlash, the columnar component that Ed discussed. And then we'll show just a little bit about what HTAP can do in TiDB and some of the capabilities built into the product with regard to HTAP. So let's flip over here to my terminal. So the first thing we're looking at here is just a big list of the instances that I've deployed. So I've deployed 16 EC2 instances. I wrote a little script that does this. I have 4 instances in each of the 4 availability zones in the US West 2 region. So let's take a look at this topology file that we're going to use to deploy the cluster. So TiUp clusters are defined in a simple YAML file. And YAML is really easy to generate using a tool. This is all dynamically generated by a tool I created. But there's nothing special in here, right? It's just a couple of real simple parameters. I'm keeping my Grafana server and monitoring stuff all in this host that I'm going to be connecting from. I have 3 of the PD placement driver servers. Those are on 3 separate nodes in 3 different availability zones. We're going to have 3 TiDB nodes. And then I'm going to have 1, 2, 3, 4, 5, 6 TiKV server nodes to start with. But we'll look at that in a little bit more detail. But let's kick off the deployment right now. TiUp cluster, deploy, I'll call it test 511, and then we give it that resources.yaml file. So the TiUp cluster deploy step is actually going to connect to all of these machines, and it's going to download all the packages we need. It's going to copy all the configuration files over, and it's going to have everything just totally ready and set up to start the cluster in a moment. So another really cool thing you can do with TiUp, I saw a question about this actually. While I'm waiting for this cluster to deploy in my cloud environment, I'm going to flip over here to my local machine where I'm going to show you this really cool feature called TiUp Playground. So this is a fantastic way to get a really easy start with TiUp. So TiUp will run on your Mac, it'll run on your Linux machine, and you can just download TiUp and install it and then execute TiUp Playground. And what that does is it will find the most recent version of TiUp that we've released, the most recent version of the TiDB platform that we've released, and it'll actually create a real TiDB cluster all running locally on your laptop. And by real cluster, I mean you're going to have a TiDB component, a PD component, a TiKV component, and I think it even starts TiFlash. So it's that easy. I mean, it takes several minutes to start up, and you can begin connecting locally to a TiDB cluster on your local laptop. So that's a really easy way to just get a quick start with it. Of course, for any kind of real usage or benchmarking, you're not going to want to do all that stuff on your laptop. But the good news is that the only step you have to take to get from this to a real cluster deployed on real machines is to make one of those resources.yaml files and start your cluster. So we've already deployed the cluster. After deploying is the process of copying the files out to the nodes in the cluster. So after that, we can start the cluster. And that'll happen just with this simple TiUp cluster start test command. So when I do this, it's actually TiUp is SSHing into all these nodes. It's starting the systemd units that were already created by the deploy process. So this is all done by creating systemd units, which means that if these nodes restart for any reason, they'll automatically rejoin the cluster. The processes will automatically restart. And that's nice to not have, TiUp doesn't have to maintain a persistent connection to all these backend nodes. It's able to just kind of let them do their own thing. After we've started the cluster, we can look at TiUp cluster display and see the status of the cluster. So that's fantastic. We see all the nodes up and running. Everything's looking great. We have our 6 TiKVs, 3 TiDBs, 3 PDs, and then our Prometheus, Grafana, and Alert Manager. I'm going to start an HA proxy instance to allow us to balance a load across the 3 TiDB server instances. So I have this really simple skeleton of an HA proxy configuration file. And then I have this simple little script. So I'm actually going to use TiUp cluster display test, pipe that through this JQ command. And that'll spit out these really simple pairs of IPs and ports. So if I just do sh proxy.sh, oops. There we go. Okay, so now we have all 3 of our TiDB servers defined in the HA proxy configuration file. So I can do HA proxy F configuration file and start that up. Great. So now we have our load balancer. We can test that by using the MySQL client, connecting to localhost, port 4000. We use port 4000 for TiDB instead of port 3306, which is the normal port for MySQL. I'm going to connect as root, and there we are. We're in. And TiDB version, so that's great. So we're all ready to go. We have our cluster running. We are connected to it. So TiUp includes a ton of other things too, in addition to just like the cluster and the playground. TiUp includes the BR tool, which we use for backups and restores. It includes the CTL suite, which is a bunch of different tools that you can use to connect to the backend components to get information about the running cluster and change some configuration parameters. It also includes our DM component, which is the data migration platform, but it also includes this really cool bench component. So TiUp bench, and TiUp just automatically downloads things when you need them. So we can do TiUp bench, we're going to do TPCC, we're going to prepare, and we'll use 64 threads. So that should be all we need to connect to the local machine by default, which happens to be where our HA proxy is running, and it's going to start firing off the prepare with 64 threads. So let's go back over and take a look in our console and just see kind of what we have going on already now. So we'll probably show process lists will probably be familiar to anyone who's used MySQL. So here we can see there's a number of processes happening, which is not quite as many as we'd expect because we're running 64 threads. The reason is that we have 3 TiDB server instances, and each of them is handling part of the load. So TiDB actually has a bunch of different information schema tables that are extensions to what you would find in MySQL. And one of those is the cluster process list table. So let's select all from cluster process list. And there we see a bunch more stuff, right? So we have 129 rows rather than the 43 that we saw without using that. Some of the other tables in here that are really interesting. So we have the TiKV store status. So the stores are the TiKV instances. And we can see that we have all 6 of those. We can see a little bit of information about each of them. And then another thing we can do that's really cool, we can actually see all of the regions. So a region, as you would have learned from Ed's presentation, is how we organize data in TiKV. So all tables, all data is split up into regions, which are typically around 100 megabytes. And if we select from TiKV region status, we can see all of the regions that are in there. So we have 821 regions right now. And you'll see that you can find information about where those are and what they correspond to. So our PPCC test is going into the test database, which is just the name of the schema. So we can do select all from there where DB name equals test, and then we can actually see how many regions correspond to the load that we're getting from the TPCC benchmark. So let's now take a look at how we can get a little bit more graphic view of what's happening in the cluster. So if you TiUp cluster display test, we see the Grafana node here. So being able to look at the Grafana dashboard is also going to be really helpful. But then we also have this piece right here. One of the PDs is the leader, that's L. So the PD itself forms a raft group, so there's a leader. But also another one of the PDs has the role of the UI. So that PD component actually hosts a TiDB dashboard user interface. So we're going to look at both the Grafana dashboard and the TiDB dashboard interfaces. So what we need to do, first of all, is map those internal IP addresses to the external IP that I'll be able to connect to here from my local machine. The Grafana one is on 10.0.21.31. So that's this IP address here. And I'll just flip over and we'll load that up. So I'm just going to log in here with the default. I think I have this battened down, so hopefully nobody's going to try to log in here and mess anything up. I don't think you'll be able to connect, but we'll see. So once you're logged in here, you can get a look at all the dashboards that we ship. So one of the really cool things about a TiDB deployment is every time you deploy, as long as you deploy the Prometheus and Grafana parts of the TiDB stack, you get this huge collection of TiDB dashboards. So we have an overview dashboard, and we have a dashboard for PD. So the PD dashboard is especially useful. This is where we can get a look at kind of the layout of all the data in the cluster. So here we can see there's 6 normal stores. Those are our 6 TiKV server instances. We have, we can see the regions that are in the cluster. We can see the number of regions. And this, of course, will be going up over time as we put more data into the cluster. I bet our prepare step has ended. So let's go see, let's go run the PPCC benchmark now. So that'll begin putting even more data into the cluster and putting more of a load onto the cluster. So back to the Grafana dashboards. Yeah, like I said, there's just a huge number of these things. So the PD dashboard has all of these different sections. You can see some of these have like 11 panels. Some of them have 14 panels. There's just a huge number of panels. Overview gives you just a little bit more information about all the different components in the cluster and how they're all looking. But then you can go over to do things like look at the TiKV details dashboard. And this is one we often use for debugging, but look at the number of these groups. So we ship a really comprehensive set of Grafana dashboards that are extremely useful whenever you want information about your cluster. And all of this is coming directly from Prometheus, which also is shipped as part of the TiDB stack. So if you have some other graphing thing, or if you want to, get other stuff directly from Prometheus, that's a totally native part of the TiDB deployment. Now let's go look at the TiDB dashboard, which is the one that's hosted by the PD component. That's this one. It's on 10.0.23.98. So 10.0.23.98 is this IP address. Okay, thanks, Google Chrome. Okay, so let's log in here. So we've got this beautiful dashboard. So this is actually a component that we ship. We've maintained this. This is software that we created. So this thing gives you right away a really amazing look at like just an overview of QPS. We can see latency, but it also shows us the top SQL statements that are being executed in the cluster. And it also shows, parses, and kind of breaks down the slow query log, which is super useful. We don't have to go use a bunch of tools and collect logs from all the separate TiDB server instances because each of those is writing its own slow query log. This allows us to actually just see this pulled together into this dashboard. And in each of these, we can see all this information about it. We can see the time it took. It really breaks it down. Coprocessor is something you'll start hearing a lot about as you use TiDB. Coprocessor is the API that's used for communication between TiDB server and a TiKV or TiFlash node. We can even see the query plan. This one's pretty simple, right? This is a really easy point select. But yeah, so this is super great the way we can see all of these flow query details right here in this dashboard. Another really cool thing in here is the key visualizer. So this shows us exactly which keys or ranges of keys are hot at any given time. So if you consider, for example, some table that has an auto increment key, if you're jamming a ton of data into a table with an auto increment, that's going to be really hot because the region's always going to be the same one. So the key visualizer really allows you to identify those situations, and we can kind of burrow down into this and see exactly what range of keys is involved. So this really helps with performance tuning. We can even see basic stuff here about the store topology. So this shows us exactly how the TiKV nodes are spread across the different availability zones that we have instances in. And now that we've gotten to that point, let's actually create some new TiKV nodes, add some more stuff to this running cluster. So we can see over here, we still have our TPCC benchmark is running. And remember, we executed that simple tie-up cluster deploy command to parse our YAML file and copy all the things out to all the nodes that are going to be parts of the cluster. But in addition, I have a scale-out.yaml file. So this file accounts for the various hosts that we haven't yet put anything onto. So I can I'm going to add 4 TiFlash nodes to the cluster, and I'm going to add 2 additional TiKV server nodes to the cluster as it's running. So this is just going to happen without interfering with any load that's on the cluster. And it's as simple as tie-up, cluster, scale out, test, and then I give the name of the file. So tie-up asks me to confirm that I want to put all this stuff on all these hosts. And I'll say, why, yes, I do. That sounds just great. Thank you so much. And it's going to, again, go download all these packages, copy all this stuff out onto all the hosts, and it's going to register all of these with the cluster. And it's going to do that without interfering with the running load. I don't have to reload anything else manually. It's just happening all by tie-up. So while we're waiting for that, I just really encourage you to go check out tie-up, and you can find it easily. Tiup.io is a really easy way to get the information about how to install that. It's a simple thing. Download a script. It's going to download a package, and then the tie-up executable takes care of everything. So, of course, tons more documentation about tie-up you'll be able to find in the documentation. So let's see, we're getting there. It's copying some stuff around. So TiFlash is a fairly complicated component. You saw that it has all of these different ports that it's listening on. There's several different things actually running to accommodate a TiFlash deployment. And we will certainly not be getting into all those details today. All right, so it's starting these up, enabling the components. Let's actually go back to our TiDB dashboard and see where we are with that. So if I reload this, hopefully we'll see some of those new items. Hey, there we go. Great. So we have our 2 new TiKV stores in the US West 2D availability zone. We also can see now that we have our 4 TiFlash nodes in the cluster. So what do we do with TiFlash now that we actually have some TiFlash nodes to actually put some stuff on? So the way we're going to make use of TiFlash, we're going to actually alter table. Let's do orders, set TiFlash replica 2. And then we'll do the same for stock. And we'll do the same for history. I'm actually not super familiar with how TPCC uses these tables, so this may or may not be super interesting. So let's just see like a really simple example of how TiFlash might be useful for a really basic query. So if we did something like select count star from orders, what do you think the explain plan for that shows that it's going to be using TiFlash? And the reason is that TiFlash is columnar. So counting the number of things in a table is super fast for TiFlash. Whereas to count the number of rows in a table for TiKV, you have to find the individual regions that are part of that table, and you have to go through each of them to find the number of current valid records. So if we do an explain analyze, that'll show us, that'll actually execute the query and show us what it's doing. So this is showing us that it's sending some stuff out to these different nodes. It shows it's using TiFlash. The formatting of this is not ideal. One thing we can do is we can give a hint, and I know ahead of time that this is not going to work as I want it to, but we're just going to execute it, and then I'll explain why it doesn't work. So we're going to try to get it to read from TiKV for orders. And that doesn't do anything. And the reason for that is that the MySQL client parses out the comments. So whenever you're trying to send a hint, you should make sure you start your client with the comments flag. So now we can see I've actually forced it to use TiKV. So before it was using TiFlash, and now I've told it has to use TiKV, so it's using TiKV to read this. So if I get rid of that, you can see that it is a little bit faster to go to TiFlash. I mean, obviously at this point in this benchmark, we're dealing with relatively low data volumes. but it actually makes a really big difference when you have a lot of data to be able to gather this type of thing from TiFlash instead of from TiKV. So if instead of just counting by orders, what if I group something? So let's see what the orders table has for us to work with. If I group by, I'm not even sure what these columns mean, but let's see what it says it's going to do if I do that. So now we have some new stuff here. We have exchange sender and exchange receiver. Those are actually a part of the MPP, or massively parallel processing feature, that's included in TiFlash. So that means that the individual TiFlash nodes are actually communicating with each other to resolve the grouping. And it means that we can push down the processing power of a query like this across the multiple TiFlash nodes. And you can see the effects of that by, there's a global variable, or rather it can be a session variable. So we can see the TiDB allow MPP, and if we set TiDB allow MPP to off and then do it, see that it's a very different explain, because it's no longer taking advantage of that massive parallel processing. It's forcing a single TiFlash node basically to do this whole work. So this doesn't really give you a flavor of the performance that you're going to see, the performance differences that you might see when using TiFlash versus TiKV, or MPP and TiFlash versus not using MPP. But what I hope this does show you is that I think in about 15 minutes, I've deployed an entire cluster that's across 4 availability zones. We have 4 TiFlash nodes and 2 TiKV nodes that were added to a running cluster, even while the load is still on the cluster. So totally seamlessly. We've been able to see in the dashboards that we can see a lot about what's happening in the cluster. And again, this is all something that we put together in like 15 minutes. So the time it takes to get you actually out and running is so easy. And it's just such a, I don't know, just a super short super short overview of what you can do with TiUp and TiDB. And that's basically what I wanted to show. It was really fast, but I'm super happy to answer any questions anyone has.
Well, thank you, Kolbe. This has been a great demo, really highlighting how easy to use the key features of TiDB. So hopefully this was a good section of the agenda today. We are now concluding the presentation part of our meetup today. And I want to welcome attendees to ask questions if they haven't had a chance to. And just a quick reminder that we do have some t-shirts for folks who are asking questions. And so we will now take questions, and we will have Kolbe and Ed answer, and some other folks on the team as well if need be. So please pipe in with questions. Thank you.